getting now into the error correction side of things. So the magic with GNSS is really this error correction. So each one of the error sources I talked about really has the potential to introduce 1 to 2 meters of error if it's really bad. Typically what we see in terms of precision with GNSS without error correction, with just like using your phone and Google Maps to navigate, we can get something like 2 to 5 meter accuracy. Typically it can be a little better, a little bit worse, depending on the number of satellites you're tracking, the location you're in, all these different kinds of things. With the error correction, we can actually get down to kind of that centimeter or sub-centimeter level in best case scenario. So it works really well. And it's really what allows us to use GNSS for these precision applications like surveying and monitoring. When we talk about the basics of error correction, there are really 3 main methods. In reality, there's only really one main method of error correction, but it's applied 3 different ways. So the most basic, maybe not the most basic, but the simplest one to explain is DGNSS, so differential GNSS, where we're taking really the difference in the error we measure and the difference in a known location and applying that offset to all of the rover units or the units connecting to that base station out in the field. RTK, or real-time kinematics, uses the same principles as DGNSS, but uses more precise timing signals from the satellite to get more accurate corrections and more accurate positions. And then finally, we have network corrections, which use the same principles as DGNSS and RTK, and introduces that idea of multiple base stations to create a more realistic error model, rather than just a simple addition or subtraction of error from an unknown location. So getting into that in a little bit more detail. There we go. So differential GNSS is the basis, it's the foundation for most of the corrections that we do. Differential GNSS really uses a base station at a known point, and then empirically measures the difference between the known point and the measured point. And then it can apply this offset to a rover unit. Typically, when we're talking about GNSS in the field, we have, for precision applications, something like a base and rover setup, where the base station is set up at that known location, and the rover unit is some sort of unit that somebody's using to mark unknown locations. So thinking about surveying like a stakeout application where you have your base station set up and you have your rover unit that's like a handheld device. You can go and you can measure locations very easily without having to lug around big equipment. And we connect the rover unit to the base station either for real-time connections with like a radio or internet connection, or we can do it post-process and just collect 2 data files, come back to the office and use a processing software like TBC and get those precise locations that the rover unit recorded based on that base station correction. So visually what that looks like is we have 2 setups here. We have the base station set up on some known location. In this example, I just put it on a building. And then we have our rover unit out in the field that's measuring a location. The location here, we'll treat it as unknown until we add that error correction, because the precision on this is super low. Again, it could be 2 to 5 meters. But what happens is, because both these stations are in similar locations, we can accurately measure the error at the base station location. So in very simple terms, we have the base station at a known point. We have the measured location of the signal. So maybe the GNSS satellites are telling us that we're 2 meters left or 2 meters west, 1 meter north, and a half meter difference in vertical. We can simply then take this error offset and apply it to our rover unit. And it's a good enough error estimation to get us a precise location. It's a very simple idea and concept where we have a base station at a known point, empirically measure the error, and then apply that same offset to the rover unit. There are some limitations. So the precision with a setup like this is typically in the half meter range, which can be a lot better than just a kind of a raw measurement coming from the GNSS satellites. And it can be good enough for a lot of surveying applications. The other limitation is that we have to be close to the base station, because this isn't going to work as soon as you get farther away than about 20 kilometers from the base station, because enough variables are changing in the atmosphere and the ephemeris and the satellites tracked and all these different influences, that the error is not going to be a realistic approximation for the actual error at the rover location. Along the same lines, we have RTK, so real-time kinematics. It uses the exact same principles as DGNSS. We have a single base setup with the rover unit connected to it. We're measuring the error, then applying that offset. The difference really comes in what signal is being received by the base station and the rover unit, so both antennas. So the satellites in orbit send a few different codes out that mark their timestamps. One is called the pseudo-random number, and that's what DGNSS uses. That's been around for a long time. It's kind of that standard civilian application for GNSS signals. The pseudo-random number is a little bit hard to explain. What happens is the satellite generates essentially an infinite string of random numbers or pseudo-random numbers, and that string is known. And so we know at some particular time a sequence of numbers is sent, however long it is and however numbers it includes. But we know that the numbers are being sent are random, so they're not going to be repeating it, so there's no pattern behind it. The sequence is stored in the satellite, and the sequence is also stored in the receiver. And because we have matching number sets, essentially, we can match those up and determine the time that that signal was sent. And then from that, we can determine the difference when the signal was sent to when it was received. This works really well, but it's also kind of limiting because you need that sequence of numbers. So the precision that you can get out of the timing is a little bit less than the precision you can get from another method called carrier phase. Carrier phase is more complicated to explain, and to be honest, I don't fully understand it. All I know is that carrier phase is much more precise than pseudorandom numbers. And if we use carrier phase for corrections in the RTK method, we can get much more accurate positions out of it. So carrier phase gets us from the half meter level down to the centimeter level, especially when we're talking about real-time corrections. In post-processing methods, we can get down to the sub-centimeter level in ideal conditions. So the carrier phase is much, much more accurate. The difference between the two goes back to some GPS and GNSS history with civilian and military applications. That could be a whole webinar all on its own, so I'll just skip that for now. But all we need to know is that GNSS and RTK use the same method. They just are based off of different signals, and that's where the difference in precision comes from. Finally, we have network corrections. So network corrections use the same processing or same principles as GNSS and RTK. The difference is that we're using multiple base stations to precisely model the error over a wider area. So the precise error can be determined at any location in the network. So instead of doing a simple offset from one base station to one rover unit, we have a network of base stations, and we can more accurately model the error as it changes with distance from each base station. If there is anybody here that uses Trimble RTX, RTX is an example of a network correction service that Trimble does. I think it's one of our best product lines. We have a bunch of base stations all over the world, and we can transmit corrections in real time, either via satellite, so transmitting directly from space to your GNSS unit, or we can do it via IP and like radio or IP and internet connection, so via like SIM card or Wi-Fi or whatever it might be. And all of a sudden you can get network corrections without having to set up your own base stations in your own network. So it can be a super convenient service added on top of your already existing like R12 or R10. Again, correction services can be its own webinar. We have a whole team that's dedicated to it, not just in RTX, but in the RTN team. If you have any questions, feel free to reach out. I can send you the right people, and we can get a more in-depth discussion going. But that's a whole different world. What that looks like visually. So in this example, we have a network with 3 base stations. You can see each is measuring their own error at a known location. So if this is a single base setup and we wanted to introduce a rover unit, what that would look like is we would apply this single offset to whatever rover unit is working in the area. But because we have a network of base stations, what we can do is more accurately model and kind of create a dynamic error correction environment. So what that looks like is if we have a rover unit, it's going to essentially have a weighted vector depending on what base station you're close to. I know the math is a lot more complicated than this, but at a simple term, if we have a rover unit close to one of the base stations, it's going to pull most of the error correction from one of the base stations. Same if you move it to the other base station, so it's going to have more of a error vector weighted closer to the other base station. If you have a bunch of rover units working in that network area, each is going to have its own kind of unique error correction based on its location. So you can see the error vectors kind of scale and change depending on the location in that network. And that makes it much easier to have much more precise error modeling because we have the availability of multiple base stations. The advantage to a network correction is that it's a little bit more precise and you can cover a much wider area. So you can realistically work in an area as large as a county or a state without having to set up all the base stations on your own. You can just connect to the local network correction services or Trimble RTX. And wherever you go, you're going to get that accurate correction. Even if you're traveling from one side of the city to another, if you're going to be traveling 100 miles during the day and it's taking out all these different positions, you're always going to have that accurate and kind of consistent error model, even though you connect to these multiple base stations.